Hi everyone, welcome to my next talk. Do you hear me? Is the connection okay? I checked it, must be okay, and I can start talking. I see your comments in the chat, so don't hesitate to ask questions or maybe suggest other topics. I have a lot of topics to talk about actually, and those one day talks are quite easy to prepare. Well, they require some time for sure, maybe several hours, but I have so much material and so much visual uh, aids so that I can speak about many different topics. Today is about design patterns in functional programming, and this is a very important topic if we are talking about functional programming as a software engineering discipline, because generally speaking, design patterns in mainstream is a well-known topic, and this area was mm, explored very long ago. We all know about the so-called book Gang of 4. It's an official title. The official title is Design Patterns, uh, something for reusable software, if I am not mistaken. So this is a very famous book, and it influenced the way we write and develop software much in a very strong way. So it was a question though. That book was describing uh, object-oriented design patterns most, but functional programming is a little bit older than object-oriented programming, and still we don't have anything nearly similar to the book Gang of 4. The question is why? Well, I unfortunately didn't prepare a slide with those books, but uh, there are several books about functional design patterns and Haskell design patterns. But those things, those books, I don't think they grasp the idea of a notion of a concept of design pattern, at least not completely. I propose a different view, a different perspective of design patterns in functional programming. And let me show you what I mean. So the first question arises is, why do we need those design patterns? What's the purpose? If we are talking about design patterns as separate notions that do not relate to anything, then sure, they are kind of a controversial topic, because people love doing much design patterns in their introduce many design patterns into their projects. But if they do this without some system, without understanding why, then we face a lot of problems, such as over engineering and too many unnecessary design patterns when it could be done simpler. So the question is, why do we need them? Well, actually, it's a part of a bigger topic that is known about. Um, uh, we can say that design patterns help us to solve typical problems with typical solutions. Why? Because it's cheaper. It's cheaper to build a project with some ideas that were well elaborated for us, rather than research everything from scratch. And design patterns are those pieces that were well thought, and they try to keep complexity low if we use them correctly. So design patterns can be very useful in practice. They can be a disaster. Oh, I'm sorry, that's a phone in my room. Let me answer it. No idea who is that. Hello. Good evening. Good, thank you. Yeah. Why did you call? That's not a problem. Right. Yeah. Yeah. That's very strange. Um, Funny. They asked, why do you keep my do not disturb for so long, like more than a day? So they are they are worried about if I am still here, if I am living in this room. But yeah, that's strange. All right, let me return to the topic. That was strange. Design patterns have their place in software engineering, and in general, it's better to relate them to some uh, methodology of developing things, so that a person could fit a specific solution uh, by knowing why and how. And I think object-oriented design is that methodology for object-oriented programming. And I propose two more uh, solutions, two more methodologies that are called functional declarative design for developing programs in functional languages with usual methods like functions, types, and something like that. And pragmatic type-level design. This methodology is for building applications with a massive involvement of type-level programming. I mean, not just using types like algebraic data types or regular data types, but rather develop some logic on the level of types, where logic is types. So I propose those two methodologies, and both of them have own ideas, approaches, and design patterns for sure. And the first thing I would like to distinguish between design patterns and design idioms, or better say functional idioms. I distinguish these two because I don't see mm, um, I see them very differently. So functional idioms is some idea, some property of a data structure, or maybe a mathematical essence of some notion, and we can turn this essence and property into a functional idiom and reuse it for other similar notions. You've heard about those idioms like functor, applicative, foldable, traversable. Functor is a property of some data structure. For example, it's a property of a list. You can map over a list, change its contents, but not the number of elements. This is what functor does. And other things also can be properties of some data structures. Foldable, traversable, as the data structures that you can convert into a single value, which is foldable, or map over the data structures and transform them in some way that is traversable. Well, traversable is a very wide notion. Those idioms are very widespread in functional world, and especially in Haskell. So you can expect a lot of them to be used for for some specific libraries. And we cannot probably even use libraries properly without those notions. This happens. But today I don't talk about them. I don't talk about functional idioms because it's a vastly different topic. And functional developers prefer to think this is patterns. They can be, it depends on how we define design patterns, but to my opinion, there are real design patterns, functional design patterns, such as high-kinded data, type selector, reader T, and etc. and etc. Let's try to draw a fine line between the two. So IDOM is an internal solution to certain types of problems. It addresses the natural properties of the object and immutable transformations of those properties. The IDOM describes what the object is and what inseparable mathematical properties it has. So IDOM is kind of essential, natural for some notion. But design pattern is different. It's an external solution to certain types of problems. A pattern is an auxiliary compound mechanism that helps to solve a problem in an abstract generic way. So design patterns describe how the system should work. In other words, design pattern can be constructed from some bits and bolts. It's not a property of a data structure. It will not exist in any form before you invent it and before you introduce. But IDOM exists in some form even if you don't know about that. For example, a functional list, is a functor, but also functional list is a monad and can be used as a monad. We call this they call this monad non-determinism. I call it enumeration, but we could not be aware about that a list is a monad. It still has this property if we are attentive enough to its properties, but we could not know about that. Well, there is no property to be for example, a design pattern reader T. There is no such property in generic structure. We use this as compound mechanism built from several different parts. So I have 3 groups of design patterns for you. Those are architectural design patterns, type level design patterns, and some other design patterns. I'm still working on this taxonomy. Not taxonomy, what is the proper word on this classification, and not sure how to call those patterns. Maybe infrastructure, something like that. I'm sure there are many more design patterns in functional programming, especially in dynamic languages, because I'm not a developer in any dynamic functional language, but still I am sure they have a lot of things to propose to even to us, to developers in statically typed functional languages. So maybe you can complete this list and propose other design patterns. Let's take a look at each of them and talk about when to use. Architectural design patterns are essentially design patterns for your application skeleton. They can shape the way you structure your project and application. And the first one is 3-layer cake. And essentially it's a division into layers. Well, maybe we can call those not just layers, but software layers. There are various layers in software engineering. Domain, business logic, persistence, application, and many others. Interop layer and many others. And this idea of 3-layer cake somehow resembles the idea of layering. So yeah, they are not called like application layer, or maybe interfaces layer, services layer, or maybe business logic, and somehow they are called differently, but I prefer to think this is a business logic layer. This is well, they call it effects, but I call it service layer, meaning that this layer has interfaces in some form, and also there is the implementation layer or application layer. They can be separate, they can be unified. This is how the initial authors proposed this three layer cake, but certainly it can be modified. Also, it is very similar to other architectures. For example, hexagonal architecture. We also see some business model here in the center. There are services around, repositories, data sources. I'm not quite sure what authors mean exactly, but maybe we can consult with such books as Domain-Driven Design, and maybe books by Martin Fowler and Bob Martin to know exactly what those things. We know what they mean, but maybe they have some additional explanation why they should be organized like this. Also, it can be seen as an onion architecture. Again, there is a domain model. The idea of those nested shapes is that the central shape should not depend on anything, and usually it is domain model, and it is kind of isolated, separated. If it doesn't know about external services, some way to keep some application structures, for example configs, or maybe application global state or something like that. If it doesn't know about those things, then it talks only about a domain, the very essence of that domain, and it's more or less pure in this sense. But certainly we need to write some business logic, and this business logic may require calling external services. This is a part of the commercial value, like calling some external services and knowing how to call them. This can be moved into the domain service layer, as this picture proposes. Well, maybe this domain service is kind of interfaces, maybe it's business logic, we don't really know. And also there are external circles and segments. What about the dependency between the layers? It's also a little bit more difficult than I demonstrated, because business logic and domain they depend on interfaces in functional languages, at least, and in three-layered architecture. They depend on interfaces and domain-specific languages, and they should not depend on implementation details. So this layer only depends on pure ideas, not the dirty implementation. And there is an implementation layer, application layer, that depends on both and runs business logic and uses interfaces for connecting to the external sources. I also proposed a so-called hierarchical free monads architecture. It's essentially the same, just interfaces, and they are not type classes. They are not any other kinds of functional interfaces, but they are free monadic interfaces, free monad EDSLs, possibly organized hierarchically, and the dependencies go the same way. This is an example on how this can be done. For example, in the Hydra framework, you can see those subsystems and free monadic languages. There is a logger subsystem, and therefore there is a logger free monadic interface for that. Same for state, same for key-value database, and there are two organizing free monadic languages. Maybe it can be organized differently, but I have specific reasons to separate those two. For example, in here we have connectivity, and here we have business logic, and like that. Also, I developed some monadic parser combinator library in C++ and based it on free monads, and I had two layers. I don't quite remember why I needed two layers, but still it is what it is. There are two layers. There is one layer of parser L, free monadic language, and another layer of parser LST, whatever this means. So I mimicked Haskell parsec combinator library with free monadic approach, hierarchical free monadic approach. But this is not the only thing that can be placed into the top layer here or into the layer here. Interfaces is a interesting topic, and we were talking about this topic. We've talked about this topic previously, so we can watch my previous talks, and I discussed several different interfaces. Maybe we can dedicate another stream for that. There is server's handle that works as an interface. It looks very much like a service locator from object-oriented programming. It is very similar to that, very similar to service locator, because we have some control structure. This control structure has methods, and those methods are interfaces to some implementations. It should be free from implementation details, but when you instantiate this handle, you fill those functions methods by specific implementations and pass it as an object. Service handle can be pure, like here, can be impure, and can do different stuff. This is not a very powerful approach, but it's very simple anyway, because defining those handles is not difficult, except when you need many of them, when you don't want to carry one big godlike service handle and you want many of them separated following the idea of interface segregation principle from solid. If you want to separate them and divide responsibilities into different service handles, then there is a question how to pass them. You can pass them as arguments plain, like one and another. You can put them into a bigger service handle pattern, and this resembles what I do with free monadic approach, with hierarchical free monads. Or you can start inventing things on the level of types to join them into some plain structure, and this makes the code much more complicated. So the simplest approach to put everything into one service handle, all the methods, all the subsystems, all the interfaces, and more complicated approaches may be very crazy. Sometimes we don't want to carry that handle manually. It's a labor work, right? And your business logic will be infected by that. At least you can use a reader tip design pattern to hide that handle behind the scenes in the context of your monadic functions. So you create a reader T environment. Well, this is the same structure mostly. I just called it environment instead of handle. Not me, but folks called it like that. And I pass it again into my business logic, but in a form of reader T environment. This is an environment, and this is my monad. So whenever I'm working with this bigger monad. It's a monadic stack here. So there is one monad, monad transformer in particular, that wraps around another monad. It can be app-l from my Hydra framework, it can be IO, most likely it's IO, and can be something else. So this is a unified monad. And when you have this unified monad, you always have the environment. You can request this environment from the context, of this monad, and this environment contains all the methods. So this is a way to call those interfaces. Again, the same problem with service handle. Well, you will have to invent a way to merge many separate interfaces, or put everything into one big environment. It's up to you, but again, it's a bit more difficult in implementation because it involves monadic stacks, but it's a little bit easier in usage, I would argue. Haskell world is not a world of one idea, so we have many for those interfaces. One of those ideas, also very spread in Scala, is known as final tagless. This approach relies on type classes or similar structures, and to define some service, you need a type class for that service, preferably one type class for one service, so like here. And then you can inject your type classes into business logic, like here. This is called an MTL style of calling things, and you can access that K service, Astra service, from your console app. I won't show how. I won't show how to fill those structures. I won't show how to implement those structures. It's just a design pattern. You can follow other resources, or you can take a look at my Hydra demo framework and see how they work, how to use them, and maybe you will see the difference between them, because all of things I'm talking about here, they all are implemented in some demo application, Astro. For your comparison, you can compare between them. And this is my idea, is to provide some knowledge and complement it with some demo applications and approach libraries and solutions, so it could be simple to compare. Yeah, what about final tagless? Again, you can add more methods into one type class, or maybe you want to have separate type classes for your separate services. This is a viable approach, meaning it follows the idea of interface segregation, the principle interface segregation. So you have many, and joining them in business logic means enumerating all those constraints. Type classes become constraints here, and this means we can access any of them. This is a not very convenient way of doing final tagless, and Haskellers will again scream at me because they think I demonstrate a wrong final tagless, as it shouldn't be done. Yes, I agree. You shouldn't do it like that, and probably you shouldn't use final tagless either. And there is even an article from John DeGoose about the death of final tagless, if I'm not mistaken. Well, if you have many services, they will be maybe I lack brackets here, but anyway, if you have many, they will be like a list on the level of types. There are ways to merge them into one type instead of many and pass this one type here. There should be more inner workings here. It should be not just a type, but maybe algebraic data type with some derivings and then certain etc. So there are solutions to shorten usage of that thing. Well, okay, I just demonstrated it's possible, and the rest is up to you. Let's move to other design patterns, this time type level design patterns. This is the topic I'm currently working on because I'm writing a book called Pragmatic Type-Level Design. It's about 80% done, so I have several design patterns to talk about. Well, high-kinded data is the idea is that you can alter some fields. Essentially, basically, when you have an algebraic data type, the types of those fields are fixed mostly, right? In any language. In C++, there is a structure, and you can have a size of int, and this will be only that field and will never change. But in languages that allow high-kinded data, you can alter fields, and the compiler will generate proper instances of your data type depending on what you passed as a type parameter. So if I asked the structure to have a unit type instead of ID, there is no ID, meaning that no ID, then okay, I will have a specific type with this unit. Or maybe I can pass some other type and get another type of the field, and etc, etc. I can alter specific fields if I need to, and can create many instances of that template type. So this is a general idea, and we can utilize this idea even further. Well, the question is why we need it. Sometimes we want to have domain types, for example, Meteor, and sometimes we want to have database types, also API types, all distinct from each other. API types can be transferred by some network. And database types can be stored into a database, and sometimes they have a vastly different structure. For example, database types should be organized in a relational way if we are talking about relational databases, and this is often not how domain types are formed. So this approach can help in reducing the number of different types in your models. You can reuse one model for everything if it fits your needs. Sometimes it doesn't fit those needs, and we can utilize the HKD design pattern even more extensively. There is a pattern I called type selector. Again, the title, the name is mine. I'm not sure, maybe someone used that design pattern before, but anyway, the idea is the same. We have some template algebraic data type, and we want to significantly alter its shape and get more specific data types. I will do it by having two dimensions of altering, I would say. First, I will mark the specific types with specific type tags. Those are type tags. I'll explain later. Also, I want to mark the usage, particular usage, as with type set marks. And when I specify two of them, I will get a set of types for specific data type I want to get. If I specify I want domain types, then okay, those things will be domain types because I can use those things as domain types. If I specify SQLite, I will get those types in the fields, and etc. for Postgres, for example. How does it look like? Again, there is a HKD template. This time it has all the fields altered because we need to substitute each type with specific external type. In general, we put here a set of predefined types. We put here the type that is about identification. We put here a type about integer, and here about timestamp. What set depends on this type parameter. So I can ask for SQLite, and will be chosen some type will be chosen specific to those SQLite marks, or domain or Postgres. And those marks are just empty data types. They don't have values. They are needed only on the type level as typeset marks and as type marks. The whole structure works because I have a specific solution called type selector type family, and you can see it as a table that matches two marks with specific types. So this type selector, as you've seen it before, it will be replaced by what is chosen by that pair. So if I specified I need domain types, those types from this pack will be chosen, and etc. And similar story here. So this is essentially type pattern matching on the type level. And yes, it involves another difficult type level feature known as type family. In Haskell, you can do it in Haskell, maybe in some other languages, but type families, I believe, they are present only in Haskell. In other languages there are macroses, or maybe template metaprogramming, something like that. So we can implement type selector with different tools. Granular type selector. Again, I want to alter my fields, but this design pattern works for different reason. Previously, we were talking about domain types or API types or the database types. They are just regular types and work as any other types. You can have values of them, you can serialize them, and etc. But in this case, we will be talking about types that have a type level representation and value level representation. And type level representation can be used with type level programming. So those type level types will be available as algebraic data types on the level of types. And this is not an easy topic because it involves many different tricks and tips, but in general I have the same idea. I want to alter fields somehow. I want to alter them for the type level, for the value level, and for the type level in Haskell I should use specific types and kinds specific to type level programming, because I cannot use string in type level programming. There are no strings on the level of types, but there are symbols on the level of types, as Haskell is called. Symbols are essentially strings, but not these strings, specific strings. The same as about integers. For value level we have int, for type level we have nat, and we can, well, I don't have a slide with using those specific strings and integers on the level of types. But I choose this specific type and depending on the level. This is why it's granular type selector, because I want to alter a field in a different way. And when I program with several Haskell extensions, data kinds, for example, I can use my algebraic data types on the level of types. Naturally, it's a level upper than what we used to do. So this is a granular type selector. Yes, it's not an easy topic, because I would, if I had the task to present you type level programming, I would start from something else, not from the granular type selector design pattern. But anyway, you can read my Pragmatic Type-Level Design book and see how it works. Let's now move to the uncategorized design patterns. There are such of them: control structure, declarative protocol, pure functor. I will not be speaking about declarative protocol or existentification and validification, but we'll show those ones. Well, the idea of control structure is simple. You define some subsystem. In this time, it's command line subsystem, and when you define it, you should get some control structure, and having this control structure, you can talk to that subsystem. It mostly works when your subsystems are actors, and this control structure is an interface to send messages and receive data from those actors, or maybe shut down them, or maybe ask them to do something. And I use this design approach many times because it's very convenient. Well, I think this is a known idea, and maybe in mainstream programming we just get some interface that communicates to that subsystem, but in our case we get some control structure. To communicate with actors, we can use mvar request response design pattern. It allows us to not miss events from from separate actors that work in own threads, and to guarantee to get messages from them guaranteed, and to be sure they processed our request. So this is a reliable way to communicate between two threads, because it is based on mvars, and if done right, mvars nicely synchronize between two threads. So there is a requester, there is a request mvar, and there is a response mvar, and there is a responder. When we want to communicate, when we want to ask the responder to do something, we put the request into the request mvar, and the responder is waiting on that mvar. It's blocked on that mvar until it's full. If the mvar is empty, the responder will wait. So when it gets full, the responder starts processing it. It processes and again puts response back into the response mvar. And again, the requester has to wait on that response mvar, and again it will be blocked unless and until the response is there. This is the simple communication idea and simple communication schema. It can be improved because there are some there are some issues with how to put something, how to declare the requests and the response, and the mvar request response pattern can be improved. Well, this is the scheme, but actually it's a bit more difficult to explain. Maybe the main difference in how we create response envar. We should send it with request envar, and we should organize requests and responses, which are separate types. We should organize them in some way. I don't have a code here. Maybe you want to consult with my other sources. This all is from my functional design and architecture book. So I have a very well explained material about that. Also, there is typed, untyped, and typed avatar design patterns. There are the two, and mostly they come together. Again, it's my design patterns and my approaches. The idea is that if we want to have some generic variable or generic data from the user, for example, a variable that keeps some user-defined state, and we have some environment, business logic, and we will need to work with those states, then we have a problem. We cannot store those state vars into a single collection, because collections are all how to say not heterogeneous, homogeneous, right? They cannot store state vars with a generic type parameter a, because a is unknown. It can be integer, it can be string, it can be anything, and type collections need to know the exact types, and sometimes we want to store them. This is where I propose this design pattern. There should be an untyped environment, in this case interpreters. In my solutions it's free interpreters, and this side is about free monadic domain specific languages. They are fully typed, they know about those A's, and they have no problem working with generic A's and generic state vars. But interpreters cannot know about those A's and should work with them uniformly. For that to happen, we can convert those state vars, or maybe only A's, into an untyped form with unsafe carriers in Haskell and with similar things in other languages, and we will get the any type, any GHC any type in Haskell, or maybe any type std any in C++, and that untyped any type can be stored in homogeneous storage. This is a very simple scheme in the diagram, but sometimes it needs a careful organization. But it works. It works in several languages even. I tried it in several places. There is an implementation of this design pattern in the Hydra framework. I use this design pattern in the custom software transactional memory library, and for something else, for parser combinator library in C++, and in many other places. So the scheme is typed untyped design pattern, and those state vars are actually a typed avatar because they don't contain the value itself. You might think, oh, that should store some A inside. No, it doesn't store data. It's a lightweight representation of your data. The data will be stored here in the untyped storage, but state var is just an accessor to that data. Well, it can have some own values inside. You can do that, but in general, it can be a lightweight accessor or key, and I called it typed avatar. The example of that will be a tvar from my custom STM library in Haskell, and tvar contains only a timestamp of some data. The tvar is created in that time timestamp, and there will be var handle that stores untyped data from the user, and tvar will only have will only be a key to access that any. So this is how I do it for soft transactional memory. Also, I would like to show you a small part of my talk at, I believe, Functional Conf in 2020. It was a remote talk because of the pandemic, and I demonstrated how to implement asynchronous free monadic framework. You naturally can have async await syntax in your business logic, and it will work nicely with free monads, hierarchical free monads. And this approach works with async values that can be awaited, right? The question is, if those values are mvars, which they are, we cannot alter mvar in a pure environment. We would like to, probably, but we need to read that mvar, and reading is not pure. Reading is an impure operation that should be done in the IO monad. So can we have async to be a functor, but do not alter its impure part? Well, actually we can. Maybe hardcore functional developers will find something wrong with this functor. I couldn't. To me, everything works. There are laws for functors, and I believe they're okay. So to make a functor from this async and to work with that in a more generic way, to alter its contents without reading, we actually don't alter the contents. We grow the function that will alter the contents when it's called. When it's called in the impure environment, and this makes the async impure variable to be a functor. So I can work with it as a regular functor. I can change the type of the internal contents. For example, it was integer, and I can alter it to string. It will rest as integer, and we'll have a function that transforms integer to string until I call specific implementation function, until I call running. In business logic, you will not see this. It will only be done in the interpreters. So this works. Yeah. And I believe this can be transferred into other impure values, such as IO, ref, and maybe something else. So it can be done. One more design pattern is about resource acquisition is initialization, which stands for A. It's a known idea from the mainstream. We typically acquire some resource by instantiation of some class, and mostly this is instantiation is done with specific language constructions, such as using in C#, but sometimes it can be done with classes instantiated on a stack, like in C++, and you do not have to worry about manual destruction of your resources. When you instantiate a class on the stack, you will get a resource, and when the control flow leaves that function, all the values on the stack will be destroyed, as well as the resource that is being held in the RIE class. For Bracket is a similar idea, maybe not quite, because we don't have classes, but the idea is similar. We can call creation and destruction of resources automatically with a bracket function. There is a bracket function that does this safely, and we can stack those bracket functions for each resource to initiate. And this looks like this. There is a bracket, it receives some creation resource function, clearing resource function, and receives what to do next. It can do more instantiation then, and finally it proceeds with some logic. This bracket function from Haskell respects exceptions and works properly with them. So if some exception is thrown from here, all the resources will be properly destroyed, or if it's called from here, same story. So stacking bracket functions is safe and convenient. And then the general recommendation is to have one only resource for each bracket. You technically you can mix create logger and create core runtime. You can put everything into one bracket, but on a careful consideration, you can find that if something goes wrong between the two, then some of those resources can hang and not necessarily be cleared. So do not mix resources in a single bracket. Use many brackets and stack them like that. Well, that's it, and I can only recommend reading my books. Again, Haskellers are still not do not recognize the value of those books yet, but actually the books have a lot of useful and very practical and sometimes even pioneering info about software design and architecture. Yeah, I expect to finish my third book, Pragmatic Type-Level Design, by the end of this year. So yes, and also this is not just a theoretical knowledge. I created many various technologies and demo solutions to back my claims. So there are, for example, demo applications which are a showcase of how to structure applications, how to build them, how to organize them, how to architecture them. Labyrinth in the Hydra framework, Astro also there, cellular application for type level approaches, Turing machine, Auction, both of all of three are from Pragmatic Type-Level Design book. There are also free monadic libraries to showcase how to use free monads, etc., etc. So a lot of stuff. That's it. I have one more slide to show to my colleagues from Haskell who constantly try to devalue free monads, and they also constantly mention that free monads are very slow and etc. Well, there are different free monads. There is a normal free monad that starts being slowing when you have around 10,000 of operations in your free monadic scenario, maybe 5,000, something like that. But church encoded free monad works fine unless you have 1 million of operations in your free monadic scenario. I highly doubt you have a business logic so long that you will have 1 million of them of operations. But and also you can break those things into separate calls, into separate business logic scenarios to not hit this limit. And again, this limit is not that difficult because the time of evaluation is 1.1, which is quite close to its counterparts, more or less. It doesn't grow like crazy. Free monad, normal free monad, stops being usable at 10,000s of operations, but those church encoded free monads are more or less the same to this moment. So yes, that's probably it. So thank you. Do you have questions? We can talk. I have time. Do you? Yeah, I believe this talk was very interesting. At least had much pleasure speaking about that. And again, functional programming has its design patterns. We just are not enough aware about them. Well, I hope when my books become more popular and spread, folks will finally see what I'm talking about. I'm talking about software engineering, and software engineering is properly understanding how to construct applications, including what is a design pattern and how to use them. Alexander is writing hi. Hi, it's the end of the talk already. But anyway, hmm. I think, unfortunately, my talks and presentations here on YouTube are not getting any mm, support from YouTube. There is a talk from Scott Blushin about functional design patterns with a famous slide uh, OOP design patterns to the left, like adapter, interpreter, and bridge, and etc., etc., etc. And to the right, functions. If you have adapter in OOP, you don't need it. There is function in FP. And again, if you have some structural design pattern from the Go book, you don't need it in functional programming. There is function. And the talk makes some point that we don't need design patterns because we have functions, and we can combine those functions to get the same behavior as design patterns in OOP provide. That's true, that's certainly true, but it doesn't mean we don't have design patterns at all. We don't need OOP design patterns because we have pattern matching, for example, instead of visitor. But still, we have a lot of various design patterns. Alexandra is asking, have you seen change set pattern in Ecto-ORM Elixir Phoenix for handling DTO differences? I haven't, but thank you for pointing to that. I probably need to let me make a note about that, because I want to collect those design patterns and maybe eventually to write a book similar to Gov. So change set pattern, okay. Design pattern in Elixir. So I mentioned the talk by Scott Lashen. That talk got more than 100,000 views. Unfortunately, my talks are not getting so much. Yeah. Alexandra is asking, do you have Labyrinth and other code mentioned in at GitHub? Yes, everything is on GitHub, and those are links. Those are links, and the link to this presentation is attached to this video. It's in the description of the video, so you can open it and click to those links, and you. And of course, OBS has crashed. Of course. Alexander is writing, thank you. Now I see slides. Yeah, you're welcome. Yeah. So, no more questions? No more comments? No, well, I won't hold you anymore and won't take your time. Thank you for your attention and see you next time. Bye. Peter Tillemans, sorry, I don't know how to properly pronounce your last name, but Tillemans says, thank you. Yeah, you're welcome. Bye.